Hello. So I apologize for having to do this lecture recorded, not in person, but I hope that you will find that it's a good lecture nevertheless. Okay, so today I'm going to talk about flexure. So this is beginning, we talked about elasticity and stiffness matrices and all that sort of thing. So today we're going to go to the sort of simplest case of looking at bending in structures. And so this is covered in chapter 8 of Centuria. There's also in the reference papers on the Smart side, there's this paper by Lengtenberg, which talks about nonlinearities and different kind of flexure designs for large displacement. This book, Rourke's Formulas for Stress and Strain, basically every sort of thing in mechanical engineering, all the structures that we want to think about, pretty much somebody wrote an equation for these things, and Rourke's formulas goes way back, so it's like more than 50 years old. But if you're interested in, bending of plates or things with holes in them and that sort of thing, you can find all those formulas in Rourke's formulas. Okay, so this is the picture that we look at, like a simplified picture of an accelerometer, right? Here's a mass and a spring here, M and K. This is the cartoon picture, and then this is the actual layout picture, for example, of an accelerometer. And so what you can see here is it's been labeled here as the x-axis, the y-axis, and the z-axis being out of the page. We will be, at least I'll try to be fairly consistent with that. So z usually we talk about is like out of the plane of the wafer. Anyway, this is a proof mass here, right? This is the thing that is m over on this cartoon over here, and then the spring thing are these two springs at the top and the bottom. And you can see in these regions here, this is the anchored part, this is the anchored part. So this whole thing is allowed to move. And so what's happened in this thing, it has moved, the proof mass has moved in the minus y direction, right? So these are anchors, an anchor here that's fixed in place and another anchor here that's fixed in place. And so you see that one spring is becoming extended in the negative y direction and the other one's becoming compressed. So this is sort of a typical way that you would see a MEM suspension moving in the x-axis. And then these are actually, the proof mass here is made up of a bunch of capacitor plates. And that's what makes up this mass M here. And really, if we want to be really careful, you notice that parts of the spring are also moving. So the spring actually has some mass to it. And we won't talk about that in this lecture, but in the next lecture I'll talk about how you deal with calculating the mass of a moving structure, right? So this is a problem. Usually we make what's, like, you think about this is a lumped element model. So all the mass is a point mass here, and the spring has no mass to it, and there's basically no stiffness in the mass part. In reality, right, that's a pretty good approximation for this structure, right, because most of the mass in this thing is really in this proof mass. And there's a little bit of mass that's moving in the springs, but we could probably neglect that. Now, there are some structures where that's not true. Like if you were looking at the vibration, let's say we got rid of this structure here and we were looking at just the vibration of a cantilever, right? So then obviously it has distributed mass and stiffness, and so we want to treat that a little bit differently. So I'll talk about some of that stuff in the next lecture. But today I'm going to go through some of the basic formulas for calculating stiffness of springs. So springs and MEMS. So basically we never make coils, pretty much. 3D structures are tough to make in planar processing. So we usually are drawing two-dimensional structures on a mask. Coil spring, right, has a three-dimensional structure to it. And there are people who have made coil springs using, for example, stereolithography. So you can imagine some kind of 3D printing processes. People have made coil springs there, but what we're going to talk about here is these sort of 2D structures that we make using lithography. And so these kinds of flexures are straightforward to make using surface or bulk micromachining. And there are some details that constrain the kind of dimensions and the type of anchors we can make. And we'll start by talking about the simplest kind of flexure, a clamped free cantilever beam, also known as a diving board. And so we draw these kinds of things in mechanical engineering. There's a clamped end over here, and then it's free to move at one end. So this part can sort of move back and forth. And there are some other kinds of supports that we talk about in mechanical engineering. Sometimes we talk about, well, we could have like a clamp beam, and we'll talk about that as well. Like, so how do you analyze a beam that's clamp? So sometimes this would be called like clamped free, and this is like a clamp beam. And I'll talk about those kind of boundary conditions in the lecture today. So here we are. Here's the cantilever beam. And so the goal, what we're going to try to do is we're going to try to find the relationship between the displacement y at x. So if I draw the coordinates here, I'm calling this x and this y. So that's the same kind of coordinate set that we had on the previous set of slides. So we've got the x-axis going along here, and x is a parameter, right? So x equals 0 is over here, and this is x equals L, where L is the length of the cantilever, and it's really said L sub c on here. And we want to know the displacement y at the end of the cantilever with an applied load F, right? Because the idea is basically F is equal to K, in this case, times y, right? Y is displacement, and so K is the spring constant. Okay, and it says we're going to make some assumptions. The tip deflection is small compared to the beam length. Plane sections, meaning normal to the beam's axis, remain plane and normal during bending, so pure bending and shear stresses are negligible. Right, so normal to the beam axis, so we're talking about like a section along here remains plane. That's what we're assuming. And if you look at the boundary conditions, they're expressed here. Y is equal to 0 at the clamp, and also the slope is equal to 0 at the clamp. So both y and dy dx are 0 at x equals 0. And then over here, well, we're actually allowed to have both slope, so dy dx and y are both non-zero at the free end. Okay, so there's nothing really specified. There's no boundary conditions that are specified at the free end. No constraints on that end. And so here's a funny picture. So checking the assumptions. So people have done, you can do mechanical testing of these structures. And so this is an example where they're bringing a probe down into contact onto this cantilever beam. You can see here, look at the base, right? It is indeed clamped. There's no curvature here, and so this support is really pretty well approximated as a clamp. And there are people, for example, there's a company in Switzerland. If you're interested, I'll dig up the name, but they make a probe like this that actually can measure force. And so you basically bring it into contact with the thing that you are measuring, and it can apply a controlled force. And so you could actually measure the stiffness. It's meant for doing this kind of testing, so you could actually measure the stiffness of your cantilever. So in particular, like if you have a structure and you'd like to know it's made out of some thin film and you don't know like what the Young's modulus of that film is, right? We've talked about what is the Young's modulus of silicon. You might be working in some other crazy material, I don't know, germanium or germanium oxide, and you don't really know what the Young's modulus is. So you can test that, right? You can make a film with a known thickness, and if you calculated what you think the spring constant is, then you can make a measurement like this and figure out the Young's modulus from that measurement. All right, so here is beginning to talk about the math. And so the basics of the math here actually come from geometry. So the idea is that we're bending this beam segment, and it's going to have some radius of curvature. And in terms of coordinates here, I'm going to draw sort of in the middle of this beam. I'm going to call that the neutral axis here. And that's really, if you look at the y-axis here, this is y equals 0. And if this beam has, what I'm going to do is I'm going to say this is y equals h over 2. And on this surface, the lower surface, y equals minus h over 2. Okay, so this total, the height of the beam along the y-axis is h. Okay, so h is height of the beam. It's the height in this direction. Okay, and we chose h. It could be like if you drew it on a mask, you might think about that as being width w, but I use w for something else, and so I'm calling it h here. Okay. And hopefully you can convince yourself that if we look at this beam, So the idea is that we have this plane that's called, and I didn't draw it very well, we call it the neutral axis. It's called the neutral axis. It's in the middle of the beam, and if you remember, strain is epsilon here. Epsilon is the x-axis strain, right? This is y and x here. So in the neutral axis, the length of the neutral axis remains unchanged, okay? And then if you just sort of convince yourself just by looking at this section of the beam, right, we can see that, so if this guy is unstretched, well, just looking at how long this curved segment is, well, it is shorter, right? So it's been compressed. And similarly, if we follow this arc out to the y equals h over 2, well, it's obviously longer, right? So if we look at the neutral axis, when this thing bent, this section actually got longer, so it's in tension, it's been stretched. And the part on the bottom here is now shorter, so it's been compressed. And so now what I'm doing here is I've got a plot here of the x-axis strain, right? So that's along this direction here, right? So here's epsilon sub x. So if we look at, and it's a little bit confusing, so y here is that this is the top of the beam here. We are stretching out the beam, so we have a positive strain here. And then if we follow along to x equals 0, this is at the neutral axis, we have 0 strain, and then the strain becomes a negative. So this is compressive, right? So it's compression here. And tension. Right, so it's easier for me to visualize this if we sort of draw it like along this plane, right? So that's what this is saying, is that the, and I'll use another color for this. So you can see this is it's being stretched here, it's being compressed. Right, so this is epsilon sub x, and it's really epsilon sub x at a given point y, okay? So we're saying basically epsilon x of y at y equals 0 is 0, and we could say that epsilon of x evaluated at y equals h over 2, that's epsilon x max. And epsilon x at minus h over 2 is minus epsilon x max, right? So the strain is, it's symmetric about the neutral axis, and it's maximum at the bottom surface of the beam. It's the maximum maximum compression at the bottom, and it's the maximum tensile at the top of the beam. And those things they're equal and opposite. Okay, so now let's look at this beam section. I didn't mean to use that color. Okay, and we have, so basically what I've done is I've drawn the beam, and now I've sort of cut it. I made a section, and so now I'm drawing. Okay, and if you remember, we had this rule that we said the relationship between stress and strain, sigma in the x-axis, is equal to the Young's modulus times the strain in the x-axis, right? And so just as on the previous slide I wrote what the strain was, here I'm going to write the stress. Here's sigma x. Okay, and remember that sigma x we think about as pressure. So it has units of pascals, which are newtons per square meter, okay? And so what you should think about is, like, if we integrated this stress over the area of the beam, right? So now what I've got, I'll kind of draw the dimensions on here. So this is h here, and actually that's not so entirely clear. Let me do it like this, right? So this guy has some height h, and we're going to say basically we have w is the width of the beam into the page. Right, so this square surface, this beam has square cross-section, so the area of this face is height times the width, h times w. And if you think about it, right, we've got stress, it's newtons per square meter, and so if we integrate this stress over this surface area, well, what are we going to get? We're going to get this integrating pressure over an area, we're going to get a force, right? And if you look at this thing, well, you could sort of imagine if you integrated this thing, it's going to integrate to an equivalent force at a point sort of along here. And this guy is also going to integrate to an equivalent force at a point that's along here. And so together, those two equivalent forces, I'll draw it on here, right? So you could imagine integrating this guy